Okay, so I warmly welcome you to this online training, Rfem 6 for students. First of all, I'm sorry for the delay. We had some technical issues regarding our GoToWebinar program. I hope you can hear me well. And today we will have the third part of our training of Rfem 6 for students. Okay, perfect. So today with me, it's also Björn Steinhagen. He will help me with the questions you will answer here to this online session. And moreover, I will be the presenter moderator of today's training. Today we will have the third part of the Rfem 6 for Student online series, and I hope you will learn something today. Okay, perfect. So I will check if Björn is already here. Yeah, Björn, you are here. Perfect. I see you. Maybe you could lose some words about you.
Yeah, sure. Thanks, Daniel. Yeah, like I said, my name's Björn. I'm having a bit of an interesting moment. I attended this exact webinar almost about a year ago as a participant and now as part of Global. And I think it's a lovely opportunity for students to just partake a little bit more and bridge the gap between what it's like studying and work in the working world. I did my bachelor's at the University of Cape Town in South Africa. I worked for 3 years in Cape Town as a structural engineer, and I just have such a love for everything digital and innovation in the world of structural engineering that I decided to do my master's at the Technical University of Munich. And that's where I find myself at the moment. I'm very happy to be here, and I hope you guys can learn a lot from the webinar today.
Okay, Björn, thank you very much for your introduction. And yeah, Björn will be today the second voice and will support me by answering your questions. And you are warmly welcome to ask any questions in Rfem 6 and we will answer them as good as possible. And yeah, so I will disable my webcam, then you can see more of your screen. So let's jump right into it. First of all, again, I'm very sorry that we had some technical issues with GoToWebinar, but now it works. The whole session will be recorded and also published on our website and on YouTube. Regarding the last online trainings about our sections, so this was the last week, we will also publish this on our website and on YouTube, and you will get the email with the certificate and also the other materials like the models this week with the email. So what can you expect today? So in general, we have this training series of Rfem 6. We started with the introduction to member design. Last week we gave you an introduction to the strength of materials, and today we have an introduction to the whole finite element method, or also called finite element analysis. So yeah, the next thing is what can you expect from today's training? So first of all, we will give you an introduction to the basic principle of the finite element analysis. Then we will model together a kind of continuous lab. It will be our introductory example of today. Then we will give you an introduction to the plate theory. So the basic different concept between two plate theories, Kirchhoff and Reisner-Mindlin. Furthermore, we show you how to perform nonlinear calculations with Rfem 6, and then the final step will be some input of singularities, what we do also together. So let's skip to the PowerPoint. So first of all, we see here the basics of FEA. So in general, computer programs are based on the displacement method. So the unknown values are deformation or displacements. It's the opposite of the force method, and both calculation and analysis methods you learn in general in the study and your college and courses. So at the force method, the force is the unknown value, and you try to get the value of the forces. In this case, we have the displacement method. So the unknown values are the displacements and deformations. And based on these things, the computer programs are calculating these deformations and displacement vectors at first, and then they can get to the results of internal forces and support reactions, for example. So, as I said, analytical solutions by hand, this is maybe possible for very easy and simple structures, but not for complex structures. So we take a deeper look that also complex and difficult structures can be calculated in a way, and this way is the finite element analysis. So it's a kind of numerical approach of getting results. So what will be done in this whole finite element analysis? The real structure is decomposed into a mesh of finite interconnected elements, and these elements, this is the finite element analysis. So we take the real structure and decompose it into a mesh of finite elements. Then at each element, the properties are described at the nodes, so also with the degrees of freedom, and then the mechanical behavior is described by different approximation sets. This is at each software developer different, and the whole process of the decomposition of structures into finite elements is called discretization. So this is one technical term you have to remember when you are dealing with finite element analysis. Okay, so the next thing is the procedure of an FEA calculation. So at first, we mesh the structure and we determine the local element stiffness relation. So at each FE node, we get the local element stiffness, and then we have to transform it to the global coordinate system. Furthermore, we have also a composition of the element stiffness relations, and then through the transformation to the global coordinate system, we assemble the entire structure. Then we have the composition of the total stiffness relation, and now we have to add some boundary conditions, and these conditions are, for example, loads and, of course, supports. So we have to consider these support conditions, and then we calculate, we solve the whole equation system, and the first thing we get is the displacement vector. And based on the displacement vector, we can calculate also the internal forces and support forces. Yeah, and this is the basic principle of the FEA calculation. You don't need to know more because I'm not a teacher or kind of prof who do courses about FEM. In my opinion, this is enough in order to know, okay, how programs like Rfem 6 work in general. Okay, perfect. So I will check our chat and try to understand if these questions are working. Maybe to some of the attendees, please write us a test question, and in order to see if it works, because currently we don't get any questions here in this chat, just to know if it works. So just any question and then we see that it works. Okay, perfect. Okay, stop it. Okay, we see it works, so perfect. So we can go ahead. In order to estimate the training and also the pace of today's training, I have prepared some polls. So the first poll is about the working with 2 screens. It would be good to know that, because then we adapt our pace to the online training. Okay, then most of you have already voted, so I close this poll and share the results. So yeah, it's a kind of 50-50, but more are working with 2 screens. So especially the first introductory example will be quite slow, because we will do it together in order to give you a rough overview about FE mesh, also the comparison of an easy example between surface and beam members. So yeah, okay, perfect. And in order to see if you have already some experiences with them, I would like to know if you have already some classes about the finite element method. Okay, perfect. Okay, so almost more than 60% have already attended some classes regarding the whole FEM topic. Perfect. So not so much things will be new for you, but also for those who would like to see something new, this training will be definitely good for you. Okay, so this will be our example. We will model together 4 surfaces. They are laying in parallel between, and then we add also another beam element, and then we cover these topics. So we apply different FE mesh sizes to each surface. Then we take a look to the convergence behavior, and on top of that, also a comparison of the results between the beam and surface elements. And then we take also an evaluation about the FE mesh size. Okay, perfect. So let's jump right into it. I will open Rfem 6. So for those people who are attending the first time of this training, I will also give you a rough overview about Rfem 6. At first, we create a new model. So I go here to the menu bar and click here on new. Alternatively, I can also click here in the symbol bar, new model. Okay, so a new window is appearing. I will close this. A new window is appearing, and we enter here the name continuous plate, and I choose here the type of model 2D XY plate. And this is everything. You can save it also under project, but in this case, I don't need it. So this is absolutely fine. Important is that we choose here the type of model 2D XY plate, because we want to consider bending moments into 2 different rotations and also 1 vertical deformation. So I click on OK. And we had already one training about the introduction of member design, where I really showed you a lot of the user interface of Rfem 6. This is something I won't do today, but I give you also a rough overview about Rfem 6. So here you find the menu bar here at the top. And important thing is that you can also change your background. So go here to display properties. And here at the bottom, you find default settings, and I prefer the white background. I'm a big fan of this white background, so I click OK, click on OK again, and then I see it like here. Okay. This is one thing, and because it's a kind of international training today, I will also show you how to change the language. So go here again to the menu bar options and click here on program options, and in the tab settings you can change the program language into different languages. Then you have to restart the program and the settings of the language were overtaken. Okay, good. So let's model together. So at first I will create the surface. I click here on new rectangular surface, and now I have to create a thickness with material and a material. So what is a thickness? A thickness of a slab or wall is pretty clear. It's here. Every surface has a thickness, and you can compare it with the cross-section of a member. Yeah. So the last time we created new members, and the members had information about the material, and this material was assigned to a cross-section. And this cross-section is an adequate example for the thickness. So we create a new thickness. And this thickness will be 300 millimeter thick. And we will also create a new material. So I open the material library. And in the material library, I can choose one of the concretes. For me, it's smoother to search for this material. So I enter here C2530, and I decide here for the European standard. I click on OK or double click here on the material, and the information about the material are chosen for this dialog. So I can also edit the material of thickness. This is now also what I want to do. Because I want to neglect the Poisson's ratio, because I want to have the results later on the calculation distributed over the whole width of the whole plate width. This should be constant. So in order to edit this, I click here on user-defined material, and now I can edit the Poisson's ratio from 0.2 to 0. Okay, I click on OK. Then I click on OK again. And now I have here the information of the rectangular surface with the material and thickness. Okay. Then I can draw it. I choose here a different view. I take a look to the view in the global Z direction. So here in the symbol bar, I find this button and I click here on view in Z direction. And now I start from the global 0 point and click on this one grid point and go 10 meters to the global X direction and 4 meters to the button. So this is the on-end coordinate. I click on OK, and right click or escape will end this command. So the next part is the creation of an additional line here in the middle, because we want to consider a continuous beam or a continuous plate. So in order to assign some line supports, I have to add here an additional line. So we can do this very easily. Just go here to the symbol bar, click here on new line, and choose here the middle point of this line and connect these to one. So in this case, I have here blue nodes. What does it mean, these blue nodes? These blue nodes have the type on line, so they are part of this line. When I double click on this outer line, number 2, I also see which nodes are on this line, and now I see here also node number 5. So it is everything in Rfem 6 is pretty clear connected with a logical behavior. So when I want to assign to one object an additional information, then you see it also here in the data navigator. Okay, so the next thing is that we create the line supports. So I have told you that Rfem 6 is structured logically. So I show you what I mean by that. I click on the left line, double click, and then I see here different options. And now I want to add a line support to this line. So I activate this option support, a new tab opens, and when going to this support, I can choose now here a new line support. In this case, I choose this hinged one. I click on OK, and you see the line support was assigned to the line. So you see that the line can have additional information, and when I click on the line support, you see also to which, sorry, this was the wrong one. And here you can see, when I take a closer look to this line, to which line this line support is assigned. And this makes it pretty easy because Rfem 6 has a clear structure of all the objects which can be connected to each other. So the other one we'll do a little bit different. So I draw a selection window in order to select both of these lines. Then I click on Assign Line Support, and Rfem 6 remembers my selection, and I create now a new line support. So I create a new line support, and in this case I only want to consider vertical forces, so it can be in the global X direction free. So I activate this sliding in X or a roller support in X direction, and this was everything. I click on OK, and I see it like that. Okay. So, and now I want to consider a surface load. In this case, we have to assign the loads to a load case. The load case can be found here in the symbol bar. I click here to this button, and I don't want to consider for this case the self-weight, so I deactivate it and click on OK again. Okay, the next thing is the creation of the surface load. So I go here to the symbol bar again and click here on new surface load. And as a load, we have here 10 kilonewton per square meter, and I assign it to that surface. I click on OK and on OK again. Okay, perfect. So by right-clicking on the surface, I can also adjust the display, so the display height of this surface load. Okay, and now it becomes interesting because we want to add different FE mesh refinements. So in general, the whole FE mesh size is set here in the menu bar by clicking on Calculate and Mesh Settings. So here we see a target length of the finite elements. If I don't do any further FE mesh refinements, Rfem 6 will generate the FE mesh by this length. Okay, but in this case, we want to do our own refinements. For a better overview, I deactivate the display of the loads and I go to the data navigator and go here to types for members. Sorry, not members, types for surfaces. And here I have the option to create mesh refinements for surfaces. Okay, right click on that and click here on new surface mesh refinement. Now a new dialog opens and I can create different kind of mesh refinements because I have here this list and then I can assign it to different meshes. So I copy this one 3 times and the first mesh refinement will be 2 meters, the second one 1.6, the third one 0.5, and the last one 0.1. Okay, I click on OK. And now these mesh refinements are blue. Blue always means that they are not assigned to any other object. So, and this is done, this will be done later on. So I activate here the load again, and now I copy the whole structure in order to make 3 more surfaces. So I select the whole structure here. Now right click on the structure, and now I want to move and copy it. I say create copy 3 times, and the displacement vector is from here to here. I can also insert here a number, but 11 meters is okay for me. I say okay, and the surfaces were copied. Okay, I move them a little bit that we have more place here. So I move them in order to have more place here. Okay. Now I will add as a reference example also the beam element. So I click here on new single member in the symbol bar. And again, here we have the member type beam, and we have to assign them a section. So I create a new section. In this case, rectangular, massive rectangle section. I go here to the parametric massive, and the geometry is here 1000 meters, and the height 300 millimeters. So wait, 1000 millimeters and 300 millimeters. So if someone doesn't see this rectangular rectangle massive profile, you can also import different sections from the cross-section library. Just click here on massive rectangle and then you have the same thing. Okay, I click on OK. And the material of the section is the same one as for the surface. This is important. Okay, this was everything. Now I create also the beam from there to there. Now I don't see my grid points. No, this doesn't matter. I can also enter here in the left dialog the member length to 10 meters. I click on OK and I see it like here. So in order to adjust maybe the work plane, I can recommend you clicking with the right click to work plane grid and then say, okay, I want to change the grid points dynamically according to the size of model. I activate this, I click on OK, and now you see it like that. Okay, perfect. So the next point is the assigning of these different mesh refinements to the surfaces. So I disable the view of the loads. And now this is one of the huge advantages of Rfem 6. I go here to the mesh refinements. I click here on edit. And now I can assign these items in the list to the surfaces, and I can remain in this window. So I click on this first one, choose this one, I click on OK, say apply, and then I jump to the other one and make this for the second one and also for the other ones. So last one, I click on OK. So yeah, okay. The next thing is that we generate the FE mesh. So in order to generate the FE mesh, we can click here in the symbol bar, generate mesh or display mesh, doesn't matter. When the mesh wasn't generated when clicking display mesh, then it generates automatically. So I click here on generate mesh. And in order to see the mesh a little bit better, I click here in the symbol bar to this one, so to the wireframe model, to the display model here in the symbol bar. And now let's take a look to the FE mesh. Yeah, this is the FE mesh, and at each FE node there will be results. And between these FE nodes and the results, they will be interpolated in order to get a smoother result distribution. So, and as you can see here, this, because we have a very rough FE mesh, we see, okay, this FE mesh and this quality is not so good. So I will expect that these results will not be so good. So let's take a different look here. Okay, this is quite regular here, and this is very fine. So yeah, okay. Okay, in order to evaluate the results with a good overview, I will create result section. So here in the symbol bar, I find the option to create a new result section. I click on that and I pick these 2 points where I want to have this section. In this case, this is this one from the left side to the right side. I click OK, and we see here this section. Okay, yeah, and this was everything. Now let's calculate, and I'm very curious about the results. Okay. Yeah, we get some we got some errors, and this is because I forgot to assign some to assign some nodal nodes here at the beam. Yeah, no problem. I have to divide this beam into two parts because I want to have here a similar way of this surface structural behavior. So right click on the member and click here divide member and choose intermediate nodes because I want to divide it in the middle of that. So I choose here 1, and now I create here also the option that the member shouldn't be completely divided, just creating this node. I click on OK. I say yes. Now I have to add the line supports. Now the same thing what we done with the assigning of the mesh refinements, we do also with the nodal support. So I go here, assign nodal support, and for my left node, I have to adjust my nodal support a little bit, because in order to also carry rotational moments, I have to consider the phi x rotation, and also furthermore that this member can't rotate around his own axis. I click on OK. I click on OK. And now I assign it to this node. I click OK and then apply again. And now I choose here this roller in X and choose the other nodes and click on OK. Okay, now I have to apply the load. In this case, I have to apply a member load. We have also line loads. Where's the difference? Member loads are applied on real members like this one, and line loads, they can be applied on surfaces. So this surface, for example, has boundary lines. When I want to apply line loads on the surface, I have to use line loads. And when I want to apply members like a steel hole with real steel cross sections, then I have to use member loads. Okay, so I click here on member load, choose here a magnitude of 10 kilonewton per meter, click on OK, choose this one, OK again, and we have this load. Okay, now I try to calculate it again. Now I hope it works. Okay, seems pretty good, and we get the result. Perfect. So at first, we take a look to the global deformation. This is one of the first plausibility checks when you are performing and doing FEA calculations, that you take a closer look to the deformations at first. So in this case, I deactivate the result section and take only a short look to the deformation. And I see here, okay, yeah, it seems quite correct. Also here, this one seems quite okay. Maybe I change here this one a little bit. And yeah, okay, so seems correct. So now it becomes very important. The next thing is the evaluation of internal forces. And therefore, I choose here these two ones. I select them and create an visibility. And I disable the view of the loads because I want to show you something. And this is pretty important that you understand that. So the members in order to see results on members, you can activate internal forces by choosing them here in the result navigator. So now you see the internal forces, so the distribution from the bending moment. And my means when I activate the local axis of this member, my means that the moment goes around the local y-axis, around the local y-axis. Remember this at members or beams. So at surfaces, we have it a little bit different. So I activate the surfaces. Also here, internal forces, mx. So mx is the same or comparable with the my of beams. So when I also here activate the local axis of the surface, at surfaces, the internal forces goes along the axis. So mx means I get the internal forces, in this case the bending moment, along the x-axis, yeah, and not around the y-axis. So this is a huge difference. So in order to see also the shear force distribution, so I have to activate this one and here also this one. Then we have here the same distribution. Okay, so this is important to remember. When I take a closer look to the internal forces of surfaces, I have to see mx as the my of beams because mx is along the local x direction of the surface. Okay, now I change the hiding of the visibilities, and now we go through the examples, and in order to have a similar distribution of the result section here on the right side, I activate the result sections. Okay, perfect. So the next thing is that I go here to the bottom part of the result navigator and I activate local extremes of the result section. So, and what can I see? First of all, let's take a closer look to the bending moment. So I choose here this one. So this beam should be our reference example. And here these surfaces should have similar values like this beam here. So let's take a closer look. So here we can see, okay, we have a support moment of minus 26 kilonewton meters, and here of minus 32, minus 31, minus 31. Okay, yeah, this seems pretty interesting because through the bad mesh refinement here, because we are very rough here, only 2 to 2 meters, we get very bad examples because only at these FE nodes the values are calculated, and the finer we get, the more we get to the same result like here at the beam element. So also here at the field moments 16, 17, and here we have 70, 53. So this is also a difference. So in order to summarize it, it is important for FE calculations that you choose the FE mesh as fine as necessary and as rough as possible. Okay, here on the left side we have it too rough, so we underestimate the results in comparison to our beam example. But when I do a too fine mesh refinement, then it costs us a lot of calculation power, and the computer is calculating a long time. So put it always also to the rentability of the whole thing in order to make your structures economically, and also consider the time for the calculation. Sometimes it is enough when you have a good FE mesh, but not too fine, but also not too rough. So a recommendation from my side is the third example. For example, here you can see when I deactivate the results that we have here, we have here more than 4 up to 6 FE elements between one span. So this occurs to good values for results. So my recommendation is between two boundary conditions, I would say, you should have at least 3 up to 4 or 6 finite elements, because then it is enough and sufficient for your FE calculation. So again, choose your FE mesh refinement as fine as necessary and as rough as possible. So now let's take a closer look to the results again. Here, right click on the section. I can open this and open a kind of result diagram. And here I can see this in a better comparison. So here you can see I have here -26 on the left side. The next one is -32 and so on. So this makes it quite interesting because the rough FE mesh is not good for this calculation. And you see also here between these FE nodes, the results are also not good, because we underestimate here a complete distribution of nodes. So when I take a closer look to the middle of one span, and this is in this case 2.5, for example, we see here that we have a value of 11.67. The same when I do this for the next surface, the same here, but now it becomes interesting. Here we have 15, so this is a quite big difference, but the value which is more correct. So in order to say what I want to say with this message is a finer mesh does not necessarily lead to better or more accurate results. This is something you have also to remember. However, FE nodes should also be close to expected extreme values, and this is important to know. Okay, one thing more, shear stiffness. In order to get here at this beam your hand calculation results, you have to consider also shear stiffness effects. So taking into account shear stiffness leads to an increase in deformation due to shear forces. So this shear deformation, especially at concrete structures, plays a major role. So it is recommended to consider the shear stiffness for the deformation analysis. So, and the standard in Rfem 6 is the setting that the shear deformation and the shear stiffness is activated for members. But in order to get the same results for your hand calculations, where you normally don't consider these effects, you can also deactivate the shear stiffness. So I double click on this member, go to the section, go here to member start and edit this, and now I can deactivate the shear stiffness. I do so. I click on OK, again on OK, and I calculate the whole structure again. And now you see how the support moment, for example, will change into that value. What would you get when you do the hand calculation? Yes, here, minus 31.25. And this is also the QL to the number of 2 divided by 8. This would be the maximum support moment of a distributed line or member load. Okay, perfect. So much to this introductory example. Before we go to the questions, I have prepared 2 polls for you. Why I say please answer this one. Okay, perfect. I will share the results. And yes, the most of you have chosen the right result. So what do I mean by discretization is the decomposition of the structure into finite elements. Perfect. So next question. Okay. Let's share the results. And again, here, the most of you, God, thank you, have chosen the correct result. So when I want to do a good FE mesh, then I have to choose it as fine as necessary and as rough as possible, or as coarse as possible. Okay, good. So let's jump to the PowerPoint presentation again, because I have told you something about shear stiffness, and this has also something to do with the plate theory. So let's go to the PowerPoint. Plate theory. So first of all, I want to take an analogy to the beam element. So we have here 2 different beam elements, so beam calculation or analysis methods. On the left side, the Bernoulli beam, and on the right side, the Timoshenko beam, also called as the deep beam theory. So what are my what do I consider here? Or what are my assumptions here? So my cross-section remain in plane. Also, the cross-section after the deformation remain perpendicular to the member axis. So here we don't consider any shear deformation. So we don't activate any shear stiffness. So we neglect also some deformation. So it's a kind of rigid shear stiffness. But when you calculate easy, simple structures with the help of some table books here, then you normally are using or referring to Bernoulli results. So, and the opposite of this Bernoulli beam is the Timoshenko beam, also called the deep beam. And there we have the following assumptions. The cross-section remain in plane, yeah, but the cross-section don't remain perpendicular to the member axis after the deformation. So we consider shear deformation, and through the shear deformation we get also higher deformation, which is also more realistic. So the shear stiffness is limited, and isn't rigid. So you can see here, we get here deformation by bending, but also deformation by shear. So maybe here a nice example on the left side, the Bernoulli beam. So it remains perpendicular to the member axis, and here at the Timoshenko beam not. Here we get an additional shear deformation angle, and this causes also to more deformation through the shear activation. Okay, now let's transfer to the plate elements. So the similar part of the Bernoulli beam is the Kirchhoff theory, and the same for Timoshenko, the Reisner-Mindlin theory. So also here some assumptions. So we have here geometrical linear solution. So we take only small deformation, the same also for the Reisner-Mindlin, also Hooke's law, cross-section remain flat, no warping, constant thickness. But Kirchhoff, no consideration of shear deformations, and the Reisner-Mindlin, there we consider shear deformation, and also transverse or lateral strains. So we have this Poisson's ratio, what we set in the former example to 0, and now I explain you also the meaning of the behavior of this Poisson's ratio. So when I pull a beam, then normally depending on the material and also the Poisson's ratio, it becomes smaller in the section. Yeah, and these effects are also taken into account by the Reisner-Mindlin theory. So let's transfer to the plate elements again. Kirchhoff on the left side, Reisner-Mindlin on the right side. So in structural analysis programs, surfaces can be calculated according to the bending theories. And we have the bending theory Kirchhoff and Reisner-Mindlin. In the calculation, according to Mindlin, shear force deformations are included, and according to Kirchhoff, they are not taken into account. So we consider no shear deformation. Therefore, it is only good for thin plates. Yeah. So it's recommended for surfaces that are relatively thin, such as metal sheets in steel construction. We only consider also a pure bending load bearing capacity, and this is also a simplified approach. So the other thing, Reisner-Mindlin, this can also be used for the calculation of thick plates, and the component of the shear influence is relatively high, so it would cause an error when we would neglect the shear force, and therefore we get also more accurate shear forces. And this theory works also with a higher value approach. So this is the difference between Kirchhoff and Reisner-Mindlin. And now I show you where you find this option in Rfem 6. So you go here to the data navigator, and here you find the static analysis settings. And when I go here to the geometrical linear setting, I edit this. And here in the tab basic settings, I find these two plate bending theories. And now remember a little bit the results. And when I change here to Kirchhoff, you will see here different results. Yeah, so different results because we are having now some thin plates, I would say. The results are quite similar, but you can imagine when we have really thick plates, like, I don't know, some bottom plates, foundation plates, or foundation plates, then the results can be different. And when we also take a closer look to the shear forces, then we see also a kind of difference. Okay, so much to the plate theory. So I have prepared a poll for you in order to summarize the theory I have explained for you. Okay, the most of you have chosen, so I close this, share the results. Okay, yes, you are right. In Kirchhoff's plate theory, we don't take into account any shear deformation. So, perfect. So, Björn, are there any questions maybe in the chat I should recap or should review and show it in Rfem 6?
I think very clear so far. Thanks, Daniel. No unanswered questions yet.
Okay, thank you, Björn. So don't be shy. If you have any questions, put it into the question box and we help you. Okay, so let's continue. The next part are non-linearities. So I go again to my PowerPoint. So first of all, I will, so nonlinear calculation. So nonlinear calculation, what does it mean? In our first online training, we have already discovered one of our nonlinear analysis. This was a geometrical nonlinear calculation. So we got the equilibrium of our results according to the second order analysis, so at a deformed structure. So when I want to do a more deeper analysis, or when I see, okay, the linear elastic behavior of some materials doesn't fit to the reality, then I have to consider nonlinear effects. So, but these nonlinear calculations have one disadvantage. And disadvantage is that the superposition law is no longer valid. This means when I want to combine different load cases or load combinations, then, and I have some nonlinear effects like tension members, something like that, then this is not possible or should be avoided. So what are typical application areas in Rfem 6? We have, as I already mentioned, geometrical nonlinear calculation, like the second order analysis. Additionally, we have also the third order analysis when I consider any tensile or membrane structures. I have also nonlinear material behavior, which is also very interesting because I have prepared here an example for you. Nonlinear material behavior is when you remember to your classes in strength of materials, how you tested them in kind of laboratorium, and you did some experiments in order to see the yield strength of a steel member. Then you can also consider nonlinear material behaviors in Rfem 6. We have also the possibility to consider nonlinear behaviors for structural objects like members, hinges, supports. And you can consider better and precise analyses and results. But remember, these kind of nonlinear effects have also a higher calculation effort. Okay, and now I have prepared some examples for you. So these examples are just for seeing and understanding these different nonlinear effects. So I go here to window, and what I have here as a first example. So I have here a frame with tension members, and this frame is a kind of a part of a completely steel hull. So we have here this one side, and you can imagine, okay, when I have here this column, that we have here also some beams for the roof, but in this case we have only this one side considered. So, and now I have to stabilize it by giving them a kind of bracings, yeah, and we see here these bracings, yeah. So what happens when I don't have here these bracings? So I delete them in order to show you what happens. Yes, or no, because we will delete them like that. Yes. So let's calculate it. We get here some wind loads, and when you see the boundary conditions, so the supports, they are supporting the structure for the Z direction and for the X direction, but not for the Y direction. So what happens? Let's calculate it. Yeah, you get an error because of an instability, and in the FE calculations, they are checking this stiffness matrices, and when they are singular, then it can be also a result that the structure is unstable. So here he writes this warning description, FE mesh node in direction Y, so it doesn't work. So how we can avoid that, or how we can make it stable, this structure, by adding some bracings. So I go here to the new single member, and here I have the possibility of giving this member type and truss only normal forces. So this member type, as we have already learned it in the first online training, carries only normal forces. It doesn't matter if they are compression forces or tension forces, but only normal forces. No bending is activated here. So, but now we give them an additional condition. So we check here this nonlinearity option. I go here to the nonlinearity tab, and I choose here failure if compression. So I edit, or I take a closer look to that. We have here different nonlinearities for members. So we have here tension, compression, slippage, tearing, yielding, and so on. For this easy example, we want to consider these members because they are bracings. They normally consider only tension forces, so they don't carry any compression loads. So they fail if they get compression. And this is also the reason why I have a bracing where I consider the tension rod from the one side and also from the other side, because the wind can blow from both sides. And this is the reason why I feel failure if compression. I click OK, and I add them from there to there. I say yes, and also from there to there. now I have to change the cross-section of these members because they are quite huge. So for that, I have another cross-section. I have here, and round rod. And now I can also copy that by drag and drop. Oh, sorry. By drag and drop. So by drag and drop. And now I calculate the structure again. And it is stable. Perfect. Yeah, this is something what I wanted to have. I changed the view into the opposite of the X direction. Now I can see it like here. And now when you take a closer look to the deformation, you see, okay, we get here the wind pressure. So it is clear that this member gets longer as well as this one. But when I take this one from the other side, so from this side, the other side of my bracing gets longer. Yeah. And this is the reason why I have here this cross bracing. So, and you see also, when I take a closer look to the normal forces, that the other one, the other member doesn't get any normal forces because this member fails because we add them here. We gave him a kind of nonlinearity, and as we can see, he got compression forces, and this is the reason why he failed and is screwed out. Okay, so much to that. We can also make an alternative of these nonlinearities of members. I select them both again. And instead of giving them a nonlinearity and deactivate it, I can also give them the member type tension, and it will have the same effect. I click on OK, calculate the structure again, and it will have the same effect. Again here. Okay, this was the first example. Next example. So sometimes it can happen that even although you have a kind of stiffening of your structure, thanks to any bracings, that this structure fails. And in order to avoid that, you can or you have to activate something in the calculation settings. So just an example of this one. So I make it normal again. So let me check. Short time. Okay, so we have here this frame with these boundary conditions, and this is here the upper beam is a truss. So a truss means that this beam has hinges on both ends, and without the bracing it would get unstable. Yeah, we can test it when I delete this and I calculate this. It has no stiffening into the global X direction. Yeah, you see it here. So we have to add them here, this bracing. So, oops, sorry. But what we have also to do and to consider is that when I take a closer look to the deformation of the structure, it will happen that the columns will get compression forces and will also get shorter, but also in the first iteration process or in the first iteration calculation, also the both bracing, so both tension rods get compression, and they would fail. So I calculate it, and let's see what happens. And you can see here we get also here structure is unstable. And now we are wondering why, because normally it is stiff, but we get here compression forces in the first iteration step. So in order to avoid this, or in order to consider this, we can reactivate kind of nonlinear members or tension members. So I go here to the data navigator, and this setting you can find in the static analysis setting. Go here to edit, and if you are when you deal with nonlinear elements, nonlinear beam elements or members, you have here a third option of reactivation. And when you accept here this exceptional handling, you have here two possibilities. I decide for this one, for the first one, that failing members to be removed individually during successive iterations. So this what this means. So after the first iteration, Rfem does not remove, for example, all tension members with a compression force at once. So it will stay at least some of these tension members, and then the other one are taken into account. So the tension member with the greatest compressive force is removed again, so at each iteration step. So let's activate this, calculate this, and see if it works. And yes, we see it works. And this is the consideration of tension members. And when you get instabilities, although you have the structure well stiffed, then it can lay on this, maybe. Yeah. Okay, next example. Nonlinear support. I have here a pretty easy example. You can assign nonlinearities also to supports. So this support is here. This is the nonlinear support. And what do I have here? I added them, and here I have chosen the nonlinearity failure if negative px. So what does it mean? So when this support gets horizontal forces against to the global x-axis, then this support fails. No support reactant will be carried. So this means, in other words, that when I pull here a force or have here a force against to the global x-axis, then this support will fail. Okay, so let's take a look to the results. So where do we have the force? We have here this force, 15 kilonewton. Maybe I can make it a little bit bigger in order to see that. Here, 50 kilonewton, and it pulls this node to the left side. So this would get negative horizontal support reactions, and negative horizontal support directions in the global x direction would fail this nonlinear node support. Okay, and therefore we have here also this fixed Hall frame, and here also we can imagine the deformation of this structure. Okay, next example. We have here a ladder with friction support. So first of all, what did I do here is that I model, or I created loads on each of these steps. Yeah, so I can show it to you. I start the animation. So each load case is one single load on one step of this ladder. And what I wanted to consider here, at which step the ladder gets too much vertical loads that this would slip to the X direction. So, and we can see here, okay, load case 1 works, 2, 3, 4, all these load cases works. But at load case 12, I guess, yeah, you see it slides to the X direction. We get too much compression or vertical forces, and this is because we have here in at the bottom 2 node supports which have a non-linearity. This is a really difficult word, I'm sorry. Yeah, so let's take a look to this non-linearity. So I added this, and here I activated a kind of friction PZ. What does it mean? When I have activated here PZ for the translational support condition, so UX, I refer to my global coordinate system, it opens a new tab here. So UX friction PZ. So what does it mean? I have here a friction coefficient of 0.2, and this would cause the maximum bearing capacity of my PX of my horizontal support reaction. So 0.2 times the PZ, so the vertical support reaction, equals this PX. So the PX, so the horizontal support force, is always depending on the friction coefficient and the vertical loads or the vertical support reaction. So, and this is something we can also see here in the support reaction when I activate them here in the result navigator. So when I have here the friction support of 0.2 times 0.5, also 0.2 times 0.5 equals 0.08. The same here, 0.09, and now 0.1, and this would lead to this slipping, because then we are higher than the 0.2 times 0.5, so the vertical load. Okay. So much to that. The next example is also a pretty interesting one. So here we have the following situation. I want to consider here a kind of plastic analysis with Rfem. So we have here this specimen. So this is something you maybe saw in a laboratory of materials when you did some experiments, and I did here the same thing. So to put it in maybe into a general concept, or concept is that the elastic deformation of structural component due to a load are based on Hooke's law. Yeah, Hooke's law is linear elastic stress-strain relation or behavior. I think this is pretty clear. At some examples, you want to take a deeper look what happens if this linear elastic or the linear stress-strain relation is not current anymore. So you want to see what happens after this linear behavior. In this case, this plastic behavior. So, and we can consider these nonlinear material effects also with Rfem 6. So how do we do that? So when we use Rfem, we have an add-on called here in the base data called nonlinear material behavior. When I activate it, I can consider elastic plastic material behaviors. Rfem 6 activates for me for materials different material models. So what do I do at first? At first, I want to calculate this surface with a linear material model. So I have already created here some material models. So double click on this surface, and here I want to consider an isotropic linear elastic material behavior. I click on OK, say yes, and the program should calculate it. And then I take a closer look to the equivalent stresses according to von Mises. So this is a kind of stress hypothesis and pretty known and also pretty used for these kind of stress designs or stress proofs for steel sections or also for steel surfaces. Okay, so we have here this specimen example with an yield strength of 235 Newton per square meter, and the tensile stress should be up to the yield strength. So maybe I'd show you also this tensile strength, this line load, and the force required to reach the yield strength of this steel surface is determined for the model as follows. So I have here normal force. The normal force is the yield strength of 235 times the area of this surface, so 30, and I get here a tension force of 7,015 Newton. Now I distribute it over the length here. So these are 40 millimeters, and I get here this line load of 5,572 Newton per meter. So I calculate it, and in order to see better results, it's important to activate here a result smoothing. Only these elements are exact the values I get in this element. So I have here constant on mesh elements. So all these values in the FE nodes are calculated, and they build the average of each element. There is no interpolation to the other element. Okay, and this is normally not the standard. The standard is this one, the continuous within surface sets, because there we have interpolations between different FE meshes. But in this one, we need this one for plastic material behaviors. And now we see here the following example. And we see here also areas which are higher than our yield strength of 235. How can I see it? I have here on the right side my control panel with different with different colors who are representing different areas of my stresses. Double click on that. I can also set here a limit, 235. This is my yield strength. I say okay. And now I see all these dark red areas which are more than 235. Interesting. So, and now you see normally it can't happen because steel is an isotropic material with a yield strength of 235, but we get stresses that are higher than 235. So to consider the real material as a nonlinear plastic material behavior, I have to activate the add-on nonlinear material behavior and also choose another material model. And this is something I do now. So I go here to, I go here to the materials, and I have to choose here this plastic material model. So double click on this one, and I have to choose here this one, plastic surfaces. When I added this, I can show you here different material models. I choose here this one, isotropic plastic for surfaces and solids. And you have here also different tabs where you can also adjust some more information like the yield strength for compression or tension. So this is the maximum value of the calculation. And then I have also here the modulus of elasticity, and I want to consider the stress failure hypothesis according to von Mises. Yeah, I do it, and now take a look what happens. I calculate all load cases because the other load case is a line load at the end, which is a little bit higher. But now let's take a look to the first load case. And now it's pretty interesting when I change here this one. The highest value, the highest result here at my stresses of von Mises is 235. So no, there's no higher value, and this is the right material behavior. And this is pretty interesting. Yeah, now you see also the places which are yielding. I can also show me kind of criteria, and these are also the location which are leading. Okay, so this shows me the degree of nonlinearity. Okay, interesting. Now, what happens when when I increase the load at the end to 505,000 Newton per meter? So now we get higher stresses because now when we take a closer look to the deformation, we see also the reduction of the deformation. So I activate the deformation at first. So this was this one. So this was to the limit, in order to reach the yield strength of this steel surface. And now we are over that. And now we see also the reduction of the deformation also here in the width. I can click here on the deformation animation and I see it here like that. It gets longer. I think this is pretty clear, but also here in the width, we see here this reduction. And these kind of material nonlinear effects you can also do with Rfem 6. Also pretty interesting for you when you are in this material laboratory and want to consider these kind of things. Okay, perfect. So let's get to another example. and to another poll. Sorry, let's get to a poll and then we do a break. So this poll is a poll with a multiple selection, so several answers can be correct. Okay, most of you have voted. Okay, share the results. So all 4 examples are correct. So you can choose as nonlinear calculations tension members, rods, so members, materials, nodes and joints, so hinges, and also when you consider geometrical the geometry and deformation according to the theory of second order, then this is also a nonlinear calculation. Okay, so perfect. So now we will do a break, and the last chapter we will model kind of singularities. So I suppose that we make 12 minutes break, that we have here in German a time of 6 o'clock, so 12 minutes, and see you later. Okay, I am back again. Björn, can we go ahead?
Yep.
Okay, perfect. Okay, so last topic, singularities. So what are singularities and where do they occur? So first of all, singularities are locations or points of a kind of discontinuity in the calculation model. So location where I can't do any plausible check with the result. So it's a kind of meaningful result. So this means we have a model problem in the mathematical or numerical Rfem model, for example, but this problem of not really interpretable results is not occurring in the reality. So at each singularity, we have infinite stresses and internal forces depending on the FE mesh. The finer the FE mesh, the higher the stresses and internal forces, and this is normally a singularity. And the mesh refinement does not improve the result. It improves only the better localization of the singularity. So what are typical singularity locations? Point and line loads, point and line supports, also openings, rectangular openings for examples, reentrant corners, so when I have sharp corners, and also stiffness changes due to material or thickness, so when there are jumps. So how can I avoid them? These two things I can avoid by our next example, for example. Yeah. And openings or reentrant corners by giving them a kind of round corner, and stiffness changes, I can avoid them by giving them over several steps with not high jumpers regarding the material or thicknesses. So now let's take a closer look to the point and line loads we can do and consider in Rfem. So for those who want to model with me, now you are welcome to do the same with me. So I go here to new and I create a new model. I go here to 2D XY plate again, and I insert here the model name singularity point load. I click on OK. And the first example is also 4 surfaces which are next to each other with a length and width of 8 times 6 meters. So I create here again a new material. Go again here to the material library, choose here the 37, choose this one, and the thickness is 200 millimeters. I click OK. And again on OK. Now I draw this surface. I go here to this direction. So I take a look to the global Z direction, 8 meters long. So X equals 8 and the Y is 6 meters, like that. This was everything. And then I create a node in the middle of the surface. So I go here again to the symbol bar, click here on new node, click that one. Right click. So, and the next thing is giving this node a point load. I go here to new node load, and in the Z direction I have 100 kilonewton. Assign it to that node. I click on OK and on OK again. Okay. So the next thing is that we assign to the lines line supports. So I select all lines. It doesn't matter if I have also selected the node or also this line load, the single load. Doesn't matter because we assign line support to lines. So only lines are interesting for Rfem 6. And I give them this kind of value. So the hinged line support. And the next the next thing is the following, that we move it to this side and copy it from there to there and from there to there, and again the same. Okay. So the next part, we create now types for surfaces. In this case, surface mesh refinements. We assign this first one to, will be 2, 1, 0.5, and the other one 0.25. So now I created this surface mesh refinement with the help of the tables. This is sometimes faster when you do the input like that. And simultaneously, these objects appears also here in the data navigator. So, and now I can, because I know the numbers of these surfaces, I can assign them very easily, because I know this is 1, this is 2, and so on. So I can 1, 2, 3, 4, and now it's finished. Yeah, very easy. Okay, and now we need a result section. So I create the result section, draw them from, draw them from there to there. I click on OK. And now I calculate this whole thing. Before I do that, I change here the name of this load case to single load, or let's say node load, or node load, sorry, node load, and deactivate the self weight. Okay, so calculate it. So now let's take a closer look to the examples, to the results. First of all, I activate here the result section, local extremes. So, and take a look to the deformation. So as you can see, the deformation looks at each surface quite okay, but not the bending moments. So let's take a closer look. You see, okay, on the right, on the left example, I have 37 kilonewton meter as field moment, and on the right side 52. So we have different FE measures, and we say, okay, from the former example, we know, okay, when I have a finer FE measure refinement, then the result are mostly better than a rough one. But which example is now the right one? Because here this example is quite okay, but here I have a difference of 7 kilonewton meters, of 45 to 52. So now I'm asking myself, okay, which field moment is now the right one? And the easy answer to this question is no one, because this is a singularity. And at singularities, the results are not useful. Yeah. So I have to see them a little bit different. Yeah, I can use these results for my further design processes or projects. So and now I have to do some things. How can I work with them? So we see, okay, this is an absolutely singular behavior. Doesn't matter if you have a rough mesh or a fine mesh. The finer the mesh is, the higher gets the results. So in the case of further mesh refinement, yeah, you can see the moment at the point load approaches infinity. So what can we do? We can distribute this nodal load to our surface load. This would be possible because we say, okay, nodal loads are deadly, I would say, for FEA calculations. So what can we do? We can distribute them to rectangular or to surface loads. How can I do that? I take here this point load of 100 kilonewton, and now I divide it by a surface area of, I don't know, 0.5 meter times 0.5 meters. Okay, so this is something you can calculate. And now let's do this. So I take here this 100 kilonewton. I have a surface area of, I don't know, 0.5 times 0.5 meters. So this is depending on the thickness to the, let's take a closer look how to explain it to you. I go here to the display navigator, I activate here the model, activate this surfaces, I click here, filled include thickness. So this is the thickness of your model. Yeah, 300 or 200 millimeters, 200 millimeters. And normally for concrete structures, we have a load propagation angle, I would call it like that, or a load distribution angle. And for concrete structures, this is 45 degrees. So when I apply the load on the top of my surface, oh, this was not the right one, this one, yeah, on the top of my surface. So here I can distribute it with an angle of 45 degrees until to the surface axis, and this is 100 millimeters. And with these things, 100 millimeters and 45 degrees, I can calculate the surface area for the distribution from a single load or node load to a surface load. I make it here a little bit easier for myself. So I take here a rectangular surface. Sorry, so in order to apply now the surface load on this surface, I need to create a new free rectangular load, because we only want to consider this rectangular load on a part of the surface and not on the whole surface. So I go here to load magnitude, and this is, sorry, before I do that, I'm sorry, I have to create a new load case. This load case is now the now I can do this. So load magnitude is in this case, let me check what I have here. My notices, yeah, 400 kilonewton per square meter. And the center and size of the rectangle is, yeah, this 0.5 times 0.5. And the center is here, this node, where we had our node load, and I refer to this surface. I click apply and next, and now you see here this surface load, so this new free rectangular load, and I do the same for the 3 other surfaces. So again, here I choose this node, choose this one, I click on OK, apply and next, and I do these for the other 2. And last but not least, this one again. Okay, perfect. So now I have these loads. I have here as a reference the node load and the rectangular load. Now let's calculate this. And now take a look to the field moment. And what do you see? Yeah, not really singularity, because at every mesh we have similar field moments, so similar results. So, and this is one approach how to avoid or handle with singularities. So, because when I take a look to this one, at one single FE node, a whole load, single load of 100 kilonewton is attacking on. So, and here we distribute these things, and there this distributed rectangular load is applying on several FE nodes, and this makes it by far easier for the whole FEA calculation. So another possibility, when I take a closer look to this nodal loads, is also to have some smooth areas. So right click on the section, I go to result diagram again, I deactivate here this one, and I can choose here a kind of smooth ranges of result diagrams. So when I say, okay, from the singularity location, I want to go 0.4 meters away to the right and to the left side, and these results I don't want to interpret or don't want to have. I can also do this here. So I go here and say, okay, the middle point is 4, so 0.5 meters away from the middle of this singularity equals 3.5, here 4.5, and the same also for the other locations. In this case, 13.5, 14.5. And I hope this will also, no, this is not correct. I have to delete this row. I have to take a closer look to this one. This is, oh, sorry, this is 12. 20, 28. Okay, now I know it. So I want to have it here at 11.5 and 12.5, sorry, 12.5, and here at 19.5, 20.5, and here at 27.5. And the length is calculated automatically, and I click on OK. And now you see here these smooth ranges and also the distributed, the distributed banding. So this is one approach how you can do this, and you can see, you can here also move this smooth area, and then the difference and also the length is appearing here, and also the results. And this is something how you can avoid that. Okay, so next example will be a similar example, but in this case with nodal support. So I click here on new window or new model again, 2D XY plate, and in this case this is a singularity. Nodal support. I click OK. And now I create again 4 surfaces, this time a little bit faster. This case a material of C3037. I click on OK. The thickness is 200 millimeters. I say OK. OK again. And the length of this is 8 meters to the global X direction, 4 meters downwards. And here we do something different. We add here a node to that coordinate, x equals 2, y equals 2. Add here a line support. And here a single support. So let's make this a little bit bigger. This 2. So and now we apply also a new surface load with 10 kilonewton per square meter. I click on OK. and I deactivate the self-weight in order to handle with the results a little bit better. And now what I do is moving this one again to the right side, to the left side, I'm sorry, and then I copy it 3 times from there to there. I click OK. So, and now we do again FE mesh refinements. As you know, it can be done very easily by types for surfaces. Go to surface refinements, click here. Sorry. 1, 2, next one is this one. So this is very fast. Here we don't have anyone. So, and when we take a closer look to the FE mesh, we generate it. We see it here. Sounds good. Seems good. And now we do again a section result. We can do this also here at the data navigator. Go here to special objects, and here you find the object or the element result section. I go here to new result section and choose it from here and create it. And now let's calculate the results in order to see if we have any singularities. And as I said before, singularities location are also nodal supports, because all the loads are on one node. So the whole material, so the whole surface as well as the whole loads are attacking on one single nodal support, which is also part of one single FE element. So, okay, deformation seems okay, but not the bending moment in X direction. As you can see here, really different values, especially at the finest mesh. We see here 110 kilonewton meter, 70, 80, 65. Now, what is the right one? No value is the right one because this is a singularity. So what can I do? Again, here I can say, okay, I can set some, when I go here to the result diagram, I can set some smooth ranges, or I consider these nodal supports as not rigid ones, but with some stiffness. Yeah, because the theory is that one, the stiffer the elements, the more loads they attract and get. Therefore, rigid support conditions like this one, like this one, are not really practical or should be handled with caution due to the likely occurrence of singularities. So we manipulate and edit now the nodal supports and giving them a kind of stiffness. And here we have the possibility to consider the stiffness via a fictitious column. So I click here, and now we can consider it like that. So I can give the column a material say, okay, which kind of model of support I want to have. In my opinion, the first one, elastic surface foundation, will give you the best results. And now I have to enter the dimensions of the column. In this case, it's 0.5, this also 0.5, and the column height. The lower the column height is, the higher is the support spring. You can remember it as a rubber you want to press. The higher the rubber is, the easier you can press it and it bends. But the shorter the rubber is, the more difficult is it to press it. So the same, it's here for the column height. In this case, I have a column height of 3 meters. Dimension are 0.5. And now I see here the calculated support springs. And I can also decide if I want to have it here, hinged, semi-rigid, or rigid at the column base. And this is the reason how I consider this fictitious column. Okay, now I click on OK, on OK again, and now you see here these springs of the nodal support. I calculate it again. And now you see here the results again. And now it's easier for you to work with the results. One thing more is that you can also do some FE mesh refinements at the nodes. Just click on one of this node and say mesh refinement, and you can do a mesh refinement, give them a mesh refinement type circular or rectangular. I choose here this rectangular. The side of this length should be 0.5, and the inner target FE length, this one, and I apply it only on this surface here. I click on OK, yes. And take a closer look to the FE mesh. And here you see this node refinement, which should make the examples more clearly. I can edit it also. I can add here this one, that it makes more accurate. Yeah. Okay. Now we have here this singularity. I did a FE mesh refinement, and now it's up to you how to watch these or see these singularities. When you have some singularities, then you have to mark them, to mark the location, and a little bit away from this extreme location where these extreme values appear, there you have to take the results for further investigations for your design. So this one exactly on the node would be wrong, but a little bit far away from that, this would be okay. Okay, and the same here, and so on. Okay. Now I have the last poll for you because we came to the end of this training. It's also a question for multiple selection. Okay. So where do singularities occur? Yeah, all 4 answers were correct. So point bearings or load applications when I have single loads, also line loads at the end, re-entrant corners, jumps in stiffness like material or also thickness, and also at the beginning and end of line support or walls. So this was it. So Björn, are there any questions in the chat? Which should we say control again?
No, I think it was very, very well explained, Daniel. There are no more questions in the chat.
Okay, perfect. Then I will show you something on our website where you can get some more information about our programs. So let me check here. So this is our website. There you find a lot of useful things for your study and also with working with our software. So first of all, here in the whole education area, you find different e-learning courses. So video online trainings recorded. We have a complete Rfem 6 for beginners course, but we have also some accomplished and recorded webinars. So when you want to go more deeply into real projects, you can watch the webinars. They are mostly around 1 hour. And when you want to have a free online course, then I can recommend you this Rfem 6 for beginners. More to that, we have also a knowledge platform where you find the first steps how to go with Rfem 6, different videos, online manuals, also some technical articles, FAQs, and also when you want to write your bachelor or master thesis with one of our programs, then I can really recommend you to do that and to submit your master thesis here at Lubel. Why? Because you get a 50 euro Amazon voucher and also can use the student license 6 months after your graduation. So this is very nice. And what I can also recommend is that we have recently started a new blog. This blog is about our company, but also about interesting things about the whole construction industry. So we have written an article about 3D printing, but also about one collapse of a supermarket center, of a shopping center in Seoul. So take a closer look, see if it's interesting for you, and read it. Yeah, so much to that. This is our website. You find, of course, a lot of other information too. What can I recommend now is as signing up for the next online training. You can find it here at online training, and the next online training will be an introduction to the material-based design like steel structures, concrete structures, and timber structures. And here you find the next online training here. So this will be now your next task. Registrate and signing up for this training, Introduction to Steel Design. Okay, so this was everything from my side. And yeah, I want to say thank you very much. And also thank you very much. Thank you very much for your attention. And let's see us on the next training. I'm really looking forward to it, and I wish you a nice week. And stay healthy. See you next time. Bye-bye.